Now let's revisit the first example we looked at, where the first time through we were only using a fixed 4 elements to look at this fixed free beam to analyze its natural frequencies. Now we're going to keep increasing the number of elements and see how our estimates of the first 4 natural frequencies are going to change. And we're going to see how does our assessment of its motion using the principal coordinate analysis change as we use a finer and finer mesh in our finite element analysis. So for some comparison, the first time we ran this, we actually do know what the analytic solution is because we have constant material, constant cross-section. So we know, at least for the first 4 natural frequencies we have calculated here, and compare it to what we got with only 4 elements in our FEA. The first natural frequency was actually pretty close, but then we saw as the estimates, as the natural frequencies increased using the FEA, it got further and further from what we knew was the actual value. So we do have the benefit in this one that we do know analytically what answer we should get. So let's see how increasing the number of elements changes those estimates and where those estimates are going to go. Looking at my version of the code for this, we're going to see we actually have, I'll start kind of on the inside of the loop, we're going to be looking at the basis of this is going to look very similar to what we saw for the fixed number of nodes. We're going to be assembling the local stiffness, local mass matrix. We're going to then slot it into the correct spot in our global stiffness and mass matrices. We're then going to apply our boundary condition. In this case, just the 1 has to be imposed, that the deflection at the left wall is 0. So whatever our stiffness and mass matrix is, we're going to chop off the first row, first column, and then we can solve for the natural frequencies, and then we're only going to track, in this example, the first 2. So the similar results are going to happen for the 3rd, the 4th, and higher natural frequencies. For this example, let's just look at 2. So that's the inner loop. That behaves basically the same we've been looking at. But what I'm doing is I'm adding this outer loop, which we'll explore in a second here. So first, a couple things in this initialization, in this, I'll call it the preamble, kind of. I am going to track every time I run my FEA code what the lowest natural frequency is and the second lowest. So the first and the second natural frequency from the FEA. Now what I'm going to do is rerun the code over and over again, and each time I'm going to add 1 more element to it, which is then going to change my approximation or my estimate of those 2 natural frequencies. I need to track their values as I go. For this example, I am going to run this end list I'm using is the number of nodes I'm going to use on any iteration. I will start by using only 3 nodes, that's 2 elements for these axial problems, up to, just for the purposes of this, 200. And then I'm going to increase it by 1. Now, we don't necessarily know how many nodes we're going to need. I'm going to use 200, and graphically we'll see what the results are. And there's nothing that says I have to increase it by 1 node and therefore 1 element at a time, but I want a lot of resolution here, so I'll stick in this example to adding 1 more element, 1 more element, 1 more element. In this problem, everything is going to have the same cross-section. We have the total length. Every element uses the same Young's modulus and the same density. So let's see what this outer loop does. This is the loop where I'm going to keep increasing the number of elements I'm using for the FEA. And I will time this just so I can also make an assessment of how long does this take to run as I keep adding nodes to it. Right, so for this outer JJ loop, my big N, that's the number of nodes I need for this iteration, I'm going to take the JJth element in N list. So that's just going to be drawing from, am I using 3 nodes, 4 nodes, etc., up to 200. Always my number of elements for these axial problems is 1 fewer than the number of nodes I have. And I'm going to pre-allocate my K and my M matrices. Here, again, the pre-allocation is important for speed, but I know that initially they're going to have the same size as the number of nodes I have. And we'll go through this in more detail as we go through kind of one iteration of this. So for this set number of nodes, that's where I get to the familiar part. I make my local mass and stiffness matrices, put it into the global, etc. And then I'm going to get my estimate to the natural frequency for that number of nodes. Then I get, and how long did it take for this iteration to run in the talk. This end then takes me back up to the top, where I then increase my elements by 1 and rerun that whole intersection again. And we'll see why this matters as we get how the values of the natural frequencies are going to change as I keep increasing how many nodes I'm using. So let me just run up to this for loop so I get some of this initialization. Let's just look here for, I'll keep it kind of small, what if JJ is the 4th time, let's say. So I just want to see on the 4th iteration, what does this look like? So let me run this. So on the 4th iteration, I'm using 6 nodes. That's already more than I used the first time. However, by this time, I've already run it for 3 nodes, 4 nodes, 5 nodes. But now we're at the 6 nodes, for example. So my number of elements is 1 fewer than that, 5. And on this run, K and M are initially then 6 by 6, because I have 6 nodes, 6 degrees of freedom. So now I'm going to run my local and my global stiffness matrices, which we've seen before. So I'll just run up to that part. So M, we have K, those are right now 6 by 6. And now I can apply my boundary conditions. I eliminate the first row, first column from M and K. So now they are only 5 by 5. I reduced it by 1, so I can only get for this iteration 5 natural frequencies. But really for this problem, I'm only going to track the first 2 every time. And always, as I add more elements, the natural frequencies that I'm going to be finding are going to increase. So I always keep adding higher natural frequencies as I go up in elements. So on every one of these, I'm going to be finding the lowest and the second lowest natural frequency, and then add higher and higher ones as I go. One thing I'll point out here in a way you can solve this, I'm actually not, as we'll see time-wise in a second, is these I can create what we call these sparse matrices. And in MATLAB, there's a sparse command built in, but in other languages, you can also do things with sparse matrices. But if I look at M here, notice I have a bunch of zeros. And actually, let me do this again for a larger value. So let's have a larger JJ. Let's just make it 10. Now, if I make it for this higher value of JJ, this is one where I'm using 12 nodes. And I assemble my mass and stiffness matrices and apply my boundary conditions. Now I have these larger M's. So now M after boundary conditions is going to be 11 by 11. So notice now how many zeros I start to have. And I only get a higher proportion of zeros the more elements I use, until most of the matrix is actually going to be zeros when I'm using a lot of elements. What sparse matrices are going to do, it's a more efficient way memory-wise to store and work with these matrices. So for example, it's commented out right now. I'll run it later, but let's just see what sparse K does. So notice if I do sparse K or sparse M, since we were just looking at M, basically what it does is, since it knows most of the values are zeros, what a sparse matrix does is it only remembers the non-zero entries, because that's going to take up a lot less room to remember the things that are not zero if we assume the rest of the matrix is 0. So basically it saves what coordinate the non-zero elements are saved to and what their values are. And we can see that finding actually the eigenvalues of sparse matrices can potentially be faster than if we don't treat it as a sparse matrix, but we're going to see it actually depends on your machine. So for right now, I'm not going to use sparse. We'll revisit in a second with sparse matrices. And then the natural frequencies I'm going to find. This is a little bit different, just how I'm writing it here so that it's compatible with sparse matrices. Really, the important part is here in what I'm doing. That's how I was doing it before. I've added this little section on so that it also will work with sparse matrices. But if you're not using sparse matrices, it'll be exactly how it looked before. And I'm going to save the lowest and the second lowest to this of the natural frequencies once it's sorted to my list. So I'm going to run this whole thing for 3 nodes to 200 nodes. And it ran, at least on my machine, fairly quickly. And Now we can look at the convergence plotting. Actually, one thing I'll note is, since I do know the analytic solutions, I am going to, in my plot, compare the ratio of the value I get from the FEA to the known value for the two lowest natural frequencies. So again, if I run this, I know the first two natural frequencies should be, from the analytic approach, 7929 radians per second, and then 23,786 radians per second. So that's what we should be getting if the FEA is working well. It should find the same solutions that we get analytically. So I'll do this convergence plot, and I'll plot it and then explain what it's showing us. All right, so what I did is I saved from every one of these runs in this previous cell up here, when I had 3 nodes to 200 nodes, I saved out of there what the estimates as to the two lowest natural frequencies were. So starting over here, when we had only three nodes, this is what we got for the black is the lowest natural frequency, red is the second lowest. In this plot, because I know the true answer, I am plotting the ratio of the FEA estimate to the analytic. So when this value is 1, that means that the estimate from the FEA matches that from the analytic. So each one of these is being divided by that same value, either 7929 or 23,786 in the case for the red line. In the next example, it will look a little bit different. But we see the trend that's happening here for just here tracking the first two natural frequencies. Omega n is pretty quickly approaching 1, meaning the FEA estimate is matching closer and closer and closer what we know is the real answer, the analytic answer. And for omega 2, the second lowest natural frequency, the same trend is happening. It also is, as I add more nodes, getting closer and closer to 1, meaning that the FEA matches the analytic solution. But notice there's a trend here. The black line is more quickly, with fewer nodes, getting close to 1 and then staying there than the second natural frequency is. And this trend is going to be upheld as I go for, if I wanted to know the third natural frequency, the fourth. They are going to converge in lowest to highest order. So if all I really care about are the first two natural frequencies, by the time I get to, let's say, around here visually 35 nodes, that I have really good estimates to the first two natural frequencies. But the third, the fourth, the fifth may not have converged yet. So I would want to plot to see that all the ones I'm really interested in have converged by then. So this till I ran it for 200 times. We see that it's basically flat, both for omega 1 and 2 after 35. So 200 nodes is, in some respects, more than I needed. But since I already ran it for 200 times, there's not much of a reason not to use the slightly more precise answer at 200 nodes than 35. Now, what could happen, you probably won't see it because you probably need very small elements, is if we really used a lot of nodes here, we might see actually an increase in the error as we got too many nodes, because the length of each element would get so small that the computer would not be able to actually remember with enough precision what the length is as we approach what we call that machine epsilon value. Probably not going to come up, but it is possible to use too fine a mesh and get those sort of errors in your answer. So the FEA is providing us basically to several digits of precision by the end here, the same results for the first two natural frequencies that we saw from the analytic. Now let's see how long it takes to actually run each of these iterations. Now, depending on what else is running on your machine, these wall time estimates may or may not be great. So for example, I'm recording this, which is taking up processor and RAM on my machine, and I have other things open, so this isn't necessarily the best estimate, but I'll at least see what it gives me. If I ran this without recording, it probably would look better, and those results are in the notes. But we see here as a general trend, this is how long in milliseconds it took to run each iteration. The fewer nodes I used, in general, the less time an iteration took. And that's because as I add more nodes, I'm making larger K and M matrices, and really what's going to be time consuming is filling in those matrices, and also time consuming is going to be finding its eigenvalues. The bigger the matrix, the longer that process takes to find the eigenvalue and to do that m inverse k, although using m\k, it is going to be faster. So in this recording, these results are not as quadratic as they would be otherwise, since so many other things are going on the computer. So this r squared is not great, but in the notes, it gets closer to 1, because roughly we should see a quadratic increase in time as the nodes increase. Let me try running it again. Sometimes it runs a little bit more reliably. All right, so we see here it's, again, not great, but we see at least an increase in the amount of time that it's taking as I add more nodes here. Try it one more time to see if it improves. All right, we're not getting a great fit here, but the general trend is it takes longer the more nodes I use. So that's the downside of using a finer and finer mesh, is that it takes longer and longer to process. Now, for this very simple problem, it's not a big deal, but if you go and have a very complicated problem or a 3D problem, it can take a long time to be running your code for more and more iterations. But what we are always interested in is checking for convergence every time. Now, I ran this before, so I knew 200 nodes was enough, but let's just say we ran this with too few. Let's say we only ran this 30 times for 30 nodes. And now we come in and we check our convergence. Now, the black line is pretty flat here, but running at only 30 nodes, we see the red line, it hasn't really gotten as flat as we wanted. I'm talking in very qualitative terms right now, but it's not convincingly flat. I'm not convinced that it has converged by only 30 nodes here. The black line, yes, it's been flat for a while, so it's converged, but the red line, not enough. So that's why you don't necessarily know up front how many to use, but what you're looking for is that flat line on the convergence, like we have here, a very convincing flat line for the two we're interested in. We have used enough nodes. So we've reached convergence with 200 nodes, at least for the first two natural frequencies, and probably by now the third and the fourth, although I'm not checking them, I really should be. But let's look at what the motion of this looks like using the principal coordinate analysis. Now this is bigger than any one we did before when we first looked at principal coordinates, because we have right now 200 roughly degrees of freedom in this system. We did eliminate one because of the boundary condition, so we have 199 nodes that we are tracking. So what we can look at here is using the same techniques that we used before with principal coordinate analysis. Nothing really has changed from the first time I did this with only 4 elements to what I'm doing now. It's just a bigger system. Right, so running this and tracking those same points I was tracking the first time I did it, the end point, the midpoint, and the quarter waypoint, we see that actually we're getting these very sharp peaks now, and this is with only the 200 nodes, but we're getting nice sharp peaks like we should be expecting. And this looks very, very close to what we got with the analytic solution using that infinite series. Now, note with the analytic method, at some point I did need to truncate my infinite series so that I could compute it. And here, a similar thing is happening. I'm only using 200 nodes, so I'm only using the first 199 natural frequencies in my queue here. So this too is truncated, and on top of that, my estimates as to what those natural frequencies are and to what my mode shapes are get worse and worse at higher frequencies. But since the power always is going to be diminishing at higher frequencies, those inaccuracies at some point start to not matter too much, because even though they're inaccurate, they're barely adding anything to my solution. So we see here, at least by eye, that this solution looks good. It looks pretty sharp. It looks a lot like the analytic solution that we had before. And what we did is we took that continuous problem. Using this FEA, I converted it into this discrete problem, or this multi-degree of freedom problem, And once it's there, it looks like any other multi-degree of freedom problem that we saw before, just a lot more dimensions than ones we've encountered in that section when we covered it.